Okay, Assalamualaikum, and I think we continue again. So we start with the well integrity challenges. As we have been talking about a lot of potential issues, the requirement for us to really maintain good integrity, setting up a good team and so on. So for the challenges, I think it's quite interesting to see the challenges itself. So in this chart, we have about 10 listed challenges. We're talking about, talking about initially the split collar. Split collar means that the casing that we run in, when we run in, suddenly because of the stretch temperature, it start to split off. So in other words, the casing itself supposed to be providing the seal to another layer of casing, to the formation, for example. But if it becomes split case to collar, there will be some additional leak passage for hydrocarbon to flow into the well. So split case collar seem to be quite common issues. But of course, nowadays we have a special design of connection. We call it premium connection, where the chances of getting split is very much less. So in the design phase, when we see the environment of high pressure, high temperature, the movement of stresses will be there. And of course, we have to put in a special connection to avoid the split collar. And for the tubular trajectory itself, talking about when it is in directional profile, we have the bending effect. For example, in the lower end of the tubing will be on tension, but the top part will be on compression. And the more stresses, the more bend, there will be more stress to the casing and the collar itself. Casing wear, as we go, when we drill well, then of course, we are running in our tubing, so on, our drill collar, that will most sometimes scratch the casing itself. The wear will be there. Sometimes, like we have seen, that wear also can be because of the corrosion from the water production, corrosion from CO2 that is coming up together with the hydrocarbon that cause corrosion to the wall thickness of the tubular. Of course, when we talk about wear, can be thickness reduction, can be a stress cracking wear, where you try to crack into the tube of the casing. For example, H2S, of the metallurgy once being attacked by H2S. So unless you use a certain material, the way they call it, the low alloy material like chrome, then you'll be able to stop that attack by the CO2. Cement channeling, like you can see that cement, when it is not properly designed, it will be cracked and then it creates a channeling. So cement, like a normal cement from you can see that the moment they put the cement, there will be some crack that can happen, and then that crack we term it as channeling. In oil and gas, like I mentioned before, we're talking about having the good cement and special cement, special additive to make sure that we have a quite reliable cement, strong cement, for a long-term requirement. 5 years, normally about 20 years requirement, or even up to 50 years requirement to retain the strength. Pipe deformation, talking about the pipe being crushed. In terms of that is normally because you have high pressure outside, then they try to really crush the pipe. This is considered like collapse pressure. That is too high because of the we call it elevated pressure happen due to temperature thermal effect. Then it's about exposing the pipe to collapse. Formation movement, normally talking about anything that we go for a certain area where the tectonic movement will be there, and we see that movement, and that movement can really push the pipe and stretch the pipe to bend, even shear the pipe when it is too strong. So that's talking about. But for us in Malaysia, we are away from the ring of fire, the earthquake, the tectonic plate. So we are a bit okay. We are not having such issue with formation movement. But some area where like America and some of the Europe area where we have the tectonic plate is happening quite frequently. Anywhere is around the area can experience the movement, the shearing effect from the earth itself. So that's the situation of formation movement. Leaks, as you can see, challenges for leaks normally because of this pinpoint hole, sometimes leaks because of this excessive corrosion, the leaks because of the split collar and so on. So the leak can be a lot, as long as you're talking about something that allow the passing of hydrocarbon, then it can be considered a leak. Like even the barrier that we put in, like the rubber packer and so on, after sometimes, because of the movement, the stresses from pressure and temperature, it create a crack. Then there will be a leak through that packer. So it's not performing as required as a barrier. It's a failure. It's a field barrier. You have a leak. And another common challenges is on the internal external corrosion. I think we have covered that. And metal loss, the thickness loss, pitting. Pitting is actually talking about the common surface issue with corrosion. When you have marine environment salt, you have oxygen, you have water, then the corrosion start to be almost exaggerated, and then it going to be eating up the wall thickness from outside. So pitting for a long after some time can cause a total failure of the casing. Like we have seen the surface casing, the conductor casing become very badly corroded and become a failure to provide the structural support to the well. Okay, then we're talking about cement, because as you know that in the well integrity issues, the well consider cement and become very critical barrier. It provide the seal for any movement of hydrocarbon between zone to zone, hydrocarbon from formation to the well. So it become a very critical to have cement to be properly placed and so on. Cement also being placed, when you run casing, we cement the casing. So when we cement the casing, we provide a total protection. We put this casing in center, and then we pump cement outside, and then we cover the cement as high as possible to surface, and then it's going to be providing the protection of the casing, because the cement actually is a very low permeability, will not allow fluid. It becomes a solid rock. It provide the some of the compressive strength to the casing. At the same time, it becomes isolation. It's some sort of like a barrier. So cement is a barrier when we run the casing and cement it, and cement also can be spotted inside. For example, spotted across the perforation, can be spotted in certain length to prevent further flow. The cement become a very critical barrier, and it's quite because it's one of the most convenient to locate or to spot the cement in the well, because you can see cement. Once we have for example, we want to seal certain leak, we can just spot the cement across the leak and try to inject the cement around the leak area, and then the cement normally will provide the sealing of the leak. So cement can repair leaks. It can even small leaks, or even for the big leak, cement become one of the barrier that going through the leak, set it, harden, and going to provide the, we call it hydraulic seal to the environment, protecting the well. So the issue with cementing casing in oil and gas is always that we have directional profile, and then with directional profile, because of the gravity, some of the casing try to go down to the bottom end. Of course, we try to push it that with the stabilizer to push it up, but because of the bending force, normally some of the cement will not be into center. When the cement is not into center, then it's going to be difficult to have good cement around the casing. So you can see some of this here, the cement is, because it's been centralized properly in vertical hole, in most cases, we have a good cement. But once you have, the hole is being enlarged, and then cement is rounded, so you can see some cement will go to the perfectly around the area, but still leaving some of the gap, small gap between the larger OD or hole. So thinking about this big channeling coming up from from the area for formation and the cement. So this is the passage of the hydraulic of the reservoir hydrocarbon coming through the through the cement. You see the channeling, it start to move up. So this is a failure of a barrier, cement in this case, to cause flow to the surface. But of course, like I mentioned, when the cement is going to one side, of course, it will allow no movement, because the cement will go to the easiest part. So you try to flow only to the easiest part, filling up the rest of the area, but you will leave behind 10% or 20% of the void, which empty with liquid. So this is where we're talking about understanding of the failure for the communication of hydrocarbon from the reservoir through to the pipe, and mostly we try to find another leak point to go through surface. And of course, we're going to handle this issue of this leak hydrocarbon to surface, or maybe some hydrocarbon flow from one zone to another. And we have to manage that issue later on. So that's why cement become very popular, easy to spot. But of course, the success of cement as barrier become important with the proper procedures and guidelines to spot the cement in place. Okay, so there's challenges of cement. You can see that, from the drawing itself, we see that the possible failures of the cement between formation and cement, between the casing and the cement itself. So all these variable of the cement potential cement failure need to be really handled. So that's why when we design a well cementing of the problem for the casing, we put a proper understanding about how to sterilize the well, how to make sure that we clean the mud cake or whatever from the wall, and so that we have a good cement contact between formation and the cement, and between cement and the casing. So all had to be intact properly. And even sometimes we blast the surface of the casing to provide some surface volume or some of the element to improve the cement bonding. So all this had to be put in place in terms of design, understanding the issues of the sealing, and of course, the failure will be there. But one thing that you realize that for us, we have seen that, if we have, let's say, a 1,000 feet column of cement around the casing, 1,000 feet, even you have about 1 feet or 2 feet of good cement around the casing, that will become a very good strong barrier to stop any hydrocarbon below that cement. Just 1 or 2 feet of good cement, because the cement is very reliable, very strong. It will help you to provide the hard seal. Okay, now we go to corrosion in tubing. You can see how the tubing can be badly corroded because of once we have the water coming in, then you have the failure in the tubing. And once you have the failure tubing here, you cannot flow because the tubing, the production start the flow. We come into the annulus and try to push the rest of the liquid downwards, if there's any leak here. But so far, you are not able to produce because most of the most of the well flow will be mixed up with the packer fluid below here, and then it start to mix up with the water coming up. So we have a problem with your packer fluid here. It's supposed to be there to protect the corrosion of both tubing and casing, but once you have a leak, then you have to shut down, and then of course you have to pull out the tubing under the term called recomplete the well. So pulling out and rerun again with the new tubing to continue your production. Okay. Now, of course, another one is this one we talk about the conductor and sphere casing. The corrosion is very bad because the effect of the marine environment at surface. This is actually close to the platform, just below the wellhead. Even it's on shore, it's just below the ground. You can see the effects of the air and the water make up the corrosion speed much longer. It's left behind is only this is, for example, the surface casing. This is the intermediate casing being corroded, too bad. What is inside is the production casing and tubing that's still able to survive, but not under high pressure. For high pressure, you need to really consider cleaning the well and rerun and then repair the top surface corrosion, and actually then you are able to produce the well again. And most of the process can take 20 days to 40 days. So you're going to impact your production. Even some of the nearby well have to be shut down because of the issue of this well impacting the rest of the well, for being produced as planned. Okay, safety valve. Safety valve is another safety valve in the tubing sink. We should be able to shut in if there's any fire on the surface. That safety valve should be sealing from hydrocarbon flow. So that's the main purpose. And most of our production, according to the Petronas requirement, always offshore in Malaysia, must be designed with the safety valve. So in the event of fire at surface, the facilities, the platform, then this valve will be automatically shut down. It will close up. But the issue is with this, this is, of course, this safety valve, is that it always be leaking because it's going to be using a flapper type of seal. So when when it is open, the flow will pass through. But if it is a fill, then the valve will close. So it's a flapper type normally. And this is going to be, for example, some flapper type because of the some of the issues of blocking or whatever. So it's sometimes it's not sealing, so it's passing through. So when you close it up, you can see the steam passing through some of the gas or oil passing through the triple SV, we call it safety valve. Then they have to repair it. Normally they will insert this is another sleeve, the temporary sleeve, a secondary barrier to close the seal and continue production. But the issue is that when you put a sleeve, then your flow area become very small, it affect your production rate. So they have to decide about how to do the repair. So otherwise they have to pull up and replace the safety valve to be able to maintain the full function of that valve to continue production. So you can see that in a surface control subsurface valve, surface control subsurface valve, we have the WR is the wireline retrievable, where you set it on wireline, and then if there's anything wrong or slinging, then you just pull up, and then you can rerun set another one. All this has been done after you clear the well, and you do the pulling up of the wireline. But this issue here, this valve is going to give you a very limited exposure of cross flow, cross area. Then they're going to impact your production rate. For example, the tubing is supposed to be able to handle up to 8,000 barrel per barrel, 8,000 barrel per day. But when you store the surface control valve, the 8,000 will become 5,000 barrel a day or even 4,000 barrel a day. Yeah? But to make a full good cross area, then you talk about tubing renewable. Tubing renewable is going to be like you're setting the triple SV as part of your tubing, so you have the biggest possible cross flow. But of course, you cannot, if it is any leak, you cannot pull the triple SV because it's part of the tubing. That's why you start to have the wireline triple to go in as a sleeve and make it an alternative or another option to operate to have this system in place for production. Okay. And then, of course, like we mentioned, we're talking about the casing pressure. Like I mentioned to you, one casing pressure can be only 1,000 psi, but because of temperature, it can go to 10,000 psi. So we have to be careful about the effect of thermal to your annual pressure. And you can see that, for example, here, when you have the tubing production, you have a high pressure production. For example, the reservoir here is about 5,000 psi. So when you have the flow at surface here at the tubing will be close to about 3,000 psi. And because of the column, holistic column. So the A can be 3,000 psi. The B, because it is being sealed properly from the water, so you might have about 1,000 psi. But C, the annulus here, C annulus, normally you have 0 psi. Sometimes you have like 100 psi because of some of the heat. Because what happens when you have smooth cement, you might have some space, with liquid. When you have that volume is too small, temperature will try to expand the liquid and make it a high pressure. So that's why what happens, see here, can be very low, like 0 psi. It can be very high, up to 500 high to 1,000 psi even, because of thermal expansion. So normally we try to have a valve here. So then sometimes they have a check valve. So when the pressure between all these valves, they go beyond the strength of the pipe here, then it will bleed off. So for example, you set A valve into up to 5,000 psi, then once the moment you see 5,000 psi start to bleed off that pressure. And so something like that. Also for B, if you set for example, you know that this annulus here must not exceed let's say 1,000 psi, then you have to set the check valve to bleed off at 1,000 psi so that you don't collapse or burst of the casing in the well bore. So that's how we manage that with the check valve. If you don't put a check valve, then of course you have to really monitor the well almost like every day to see the pattern of moving of pressure increase due to production or due to shutdown and some other reason. Okay. So now we go to the next slide. We're talking about the scale. You know what happened? Well integrity actually is not really directly impact the scale, because the scale actually reduce your production. Scale is like cholesterol in your bloodstream. Cholesterol means that you have to have accumulation, and then the flow area become restricted, then sometimes when the skill is going too extensive, it's actually blocking the drill string. So when blocking the string means you don't have no production. So normally we start to see the production being declined. You see, maybe it's the reservoir behavior. But actually, the tubing having scale, build up of scale like cholesterol we call it, and then the ID or the flow area becomes small. So you have less production, but it's not because of reservoir, because of the scale formation in your tubing. So you can see there's a various scale experience in our production, oil production or gas production. The calcium carbonate start to accumulate inside your tubing. Sometimes the calcium, we call it calcium sulfate. We have the gypsum, all these things, and even there's iron compound. So what popular is call it, all these system here. Sometimes the build-up of this cake is getting harder because with harder material, you just cannot clean with your, with your tools, the wireline tools, because you're going to be too light to crush the hardened scale. So what we do actually, we go with the coil tubing. Coil tubing, we have drill bit, and the drill bit try to mill through the scale going downhole. So normally the scale getting softer as you go deeper because it's still with the temperature stumbling up with the building up the strength. But once you go at surface with the lower temperature, it start to harden very hard. Even some of the scale go to the flow line and start to block the flow line. So normally what we do is just shut down the well for a while, take out the flow line and replace with a new one. Normally that's the case. So, but every time that you do, you have to shut down the production. So that's always an issue by management to allow you to do that, or you do it in a planned manner. Like do it, for example, 3 wells have the issue. Then you plan for the repair job within the 3, to make it 3 wells program for well intervention. Okay. And then, of course, this is our build-up scale. You can see some scale is quite still reasonable. It can still produce, but the amount of scale is still there to to block your flow line, to cause your surface equipment, your separator to have all this scale building up. But this is an example where scale is building up slowly that you have reduced the flow area. That if the well is producing, let's say 8,000 barrel, suddenly it's reducing to only about 2,000 barrel. So this is sometimes we don't see that clearly unless we run and check, check the ID of the casing, that we realize that if we are not able to pass through certain depth because the scale at that moment is getting very severe. So this is the condition of scale building up too far. Even come to a situation, it come to a very close ID, actually plugging off the tubing totally. Yeah. So that's how it looks like for scale. For HPHT well, actually the plugging is not that easy, because you're going to be dealing with temperature and pressure. So sometimes you see that you put a plug, the plug start to leak. And then when you are dealing with, we are dealing with everything is on high pressure testing, high pressure tools, and so on. So you have issues when you're talking about this plug element on HPHT well, because some of the area or reservoir still virgin, still new. So you're talking about depleted reservoir, but still some area still have the no high pressure like before, original pressure. Then you have to manage that properly. At the same time, when we talk about plugging, you can see that because the aging, we plug the well after 15 years or 20 years, the condition of the well, the corrosion will be very bad. So we have issues to manage our integrity before we really finalize our plug environment, because involved with management of high pressure in this area, and then at the same time the temperature. Okay. And then of course now we go to common well integrity. So if you have any question, then I'll try to see, and if you have any, then I'll try to answer that. So any question from the floor? So we have Noraisha, we have Omar, we have Azuno, we have Hidayah. Any question? Okay, now let's proceed. So we have about 40 slides to go. Okay. So I think we try to target our, our class here, our course here up to 1:30. So we targeted for 1:30 lah. Okay. So you can see that we talk about the common well integrity failure. Before we talk about the challenges, now we're talking about what is common in the failure. So that once we know what is common, then of course when we do the planning, you do the design, we know what area to focus. Based on the study, global statistics, based on the literature in the internet, we can see that well, talking about the tubing is the main core because it's the most stressful area of the well. So this is where we talk about understanding that tubing become very really high frequency of failure. And then we're talking about the next one, is conductor. Can you will see the corrosion, conductor corrosion itself. And then we have talking about the rest, like the casing itself, some of the wellhead, the design flaws. We have some cement issues. So we can see this is the common, but our focus is only the first three, the first four. We have the tubing, we have the conductor that is an issue, we have the safety valve, and then we have the casing. So this is going to be the popular area where failure can happen. So most of the engineer, we try to focus on the design of this area and then try to, even we have to spend more money, it's okay because you're talking about the life of the well, because the longer we can sustain the well for production, the better economics for the well, more money for the company. Okay, now we go about the common issues, now we're talking about one by one, but talking about combination. If we go and try to produce the well, and then you see record of the potential issue with integrity. We talk about the annulus pressure, high annulus pressure, the scaling effects of the well, the corrosion, and the leaking triple SV, the failed SB, the control line being crushed, all these things become the issue of integrity. Because when the control line is crushed, in other words, you're not able to operate the triple SV, so the well is exposed to danger of not able to close in case of emergency. So you can see all these elements here, like corrosion in tubing, and then talking about the surface casing corrosion, all can happen in one place because of the aging. So it's going to be difficult. Even like a few of this combination, we make sure, we ask, they request you, demand you to shut in the well because it's not safe to produce. So you can see the element of failure is a lot, scaling and so on. So this is the area we're talking about. We are not really planning the well to handle this issue. This is what is going to happen. Multiple failure that you have to shut down the well and do a repair job. To repair job means that we have to really go in, fill the well, and then try to pull up the tubing, investigate the casing here whether the thickness is still there. And with this thickness is not there, we're going to run another casing to case off this area and run a smaller tubing and complete the well, with something smaller because of the requirement to set another casing to seal off the leak of the, we call it production casing. But if the production casing is intact, just a matter of replacing the tubing, then you're back to normal to produce. But of course, to do that, you have to repair all the leaks that is going to be there. For example, if there's a leak over here, most likely they're going to perforate through, you try to squeeze cement and try to seal the area here, because you have the access now. And then once you are able to solve all the issues, then you run the completion, produce the well as normal. So that's the step of how to handle the issues with well integrity. This is one example of surface casing burst. Like this is the case, I think, sure whether it is this is should be actually something in the sea, if I'm mistaken. What happened actually is it's onshore well. So the annulus pressure, like I mentioned to you, is about 1,000 psi. Because of the temperature, it start to shoot to 10,000 psi. It bursts the casing, and then when they pull out the casing for to understand the issue, they see the burst effect. So this is because of the thermal pressure increase, from certain psi to 7,000 psi, you start to burst the casing. So this is the one example of the temperature impact on the pressure in the annulus, collapsing the casing. Okay, now annulus pressure, I think that's what being described to show the impact of the annulus pressure from 2,000 psi because the pressure temperature rises from 45 to 115. Then it create expansion of liquid pressure because 7,700 is burst the casing. Okay. Okay, now we go for what is the potential leaks in the well bore. So this you can see the potential leak can be a few here, but all possible leaks, Anything you have metal, you have corrosion effects, you have wear effects. Then you're talking about mechanical effect like parted collar and so on, And then talking about attack of H2S or even H2S can even, damage the tubular quickly. So of course, we have to see how to manage that with the barrier. But some barrier normally can handle those leaks. For example, you have a leak there, the primary barrier failed, for example, but you have the secondary barrier to protect the surface from flow of hydrocarbon to surface with the secondary barrier. So that's why all this potential leak, we have to check for the barrier, the primary barrier and the secondary barrier, and those barriers should be able to protect us. If there's any leak, you still can continue producing the well safely. Yeah. Okay. And then one interesting part is actually the conflict of interest. When they want to produce more on the wellbore, they start to have a lot of jewelries to the completion. They have so many packers and there's so many, tools, elements, control system, and so on. And then what happens when you're running systems? So the drag will be more with all those components installed. So the chances of putting up to the bottom is not going to be 100%. Sometimes it's being stuck halfway before going to the end. At the same time, they're putting too much accessories. They start to create some leak, potential leak. The more tools you have, the more chances of leak happening in the packer system. So of course, intention is to have good production, but you are exposing yourself to potential leak. So there must be a balance. For example, a completion jewelry coming up in line, you say that, okay, if you want to do this, how are we going to handle the potential leaks? If there's a way, and then both teams agree that it's acceptable and they have a method to seal that leak, of course, then it's going to be happen. Otherwise, we try to modify the completion string to be able to manage our well integrity issues in the future. Okay. Okay, that is what happens if you fail. Well integrity failure can cause, injury and loss of life, damage to asset. Okay, for example, in Piper Alpha before, because of the, so much pressure being built in and not able to close in. And even the triple SB supposed to be closed in, but the management said no, they still have their commitment to produce. So suddenly it just caught on fire. Then the Papa Alpha actually burn out. They burn out the platform, and I think they have lost quite a few number. And recently in 2010, I think the famous Mocondo in the Gulf of Mexico in America, where they think they're talking about the loss of huge amount of oil spill. I think they have to spare, for example, BP, the operator of the area, they have to save about 15 billion in their asset just to cover the legal expenses. 15 billion US dollar is huge loss. So you can see that the moment integrity failure, the disaster will be very much expensive. It will cost the operator to go bankrupt. So because of the failure. So this is the impact. It's huge impact. Okay, for this second session, I think we'll continue because I think we missed that. Okay, now for the integrity nightmare. So like before, we have seen the drawing. So this example of the Montara blowout, East Timor Sea, this is close to Australia. So this is about 7 days being leaked. So they have about, if the well flow at 2,000 barrels per day, so it's quite a huge amount of barrel of oil being spilled out. And they have to kill the well by using a drilling from one side and then try to kill from bottom, and then to stop the flow. Because this production is coming from a big reservoir. So you just imagine that, it's indicating the amount of oil from the reservoir, from high pressure reservoir, and then the oil is continue flowing until you kill them from a distance with relief well, we call it. The root cause is actually about hydrocarbon enter through the non-fine instrumental. So in other words, the whatever actually the non-flash method is not sealing the hydrocarbon zone. Hydrocarbon zone try to go through the non-flash casing, and it go through to up to the casing into the, we call it this is going to be intermediate casing, and then the area there is not able to have any control, because it's just what you have is only the wellhead area, and because the pressure is too high, you start to already uh, have a push through or whatever the system at the wellhead, and then when you have a spark, you have a fire. This is integrity because of cement fill to seal the reservoir itself. Okay, this is Mokondo that you can see. The huge amount of fire because of the big production from this receiving platform. You drill a well, then and of course you're going to have the well completed. This is the last well drilled, and they have the problem with the last well, and it affects all the well around. So over here is about 5 million barrels of oil being discharged. 5 million barrels is huge, in terms of the oil spill, the pollution from the area, and about 50, I think about 87 days of the flow of the gas. This is in April 2010. So you see the impact of integrity, huge, very expensive. It can make you bankrupt. Okay. So we start to understand the integrity by understanding Mokondo. Because Mokondo itself involve a lot of studies, research. Even the politicians start to come in, and the experts also try to understand what's the issue, because we want to learn. This is a critical issues, and then what we can learn to improve our well integrity planning and management. So from here you can see that the hydrocarbon have to go through the whatever we call it, the tubing itself, and then what happen? They have all the barrier in. They have the cement to isolate the hydrocarbon, and they have the cement erosion to check to make sure the cement is good. They have well integrity, task being implied. And of course, they have monitoring done, the BOP is there, but cement evaluation tool, this is the missing link. Because when they have filled that, then the hydrocarbon will try to go through. And then with all the elements of uncontrolled BOP cannot seal, then they have a blow up. This is the uncontrolled event. So this here is controlled. The barrier is, and then when you fill the barrier, then you are not able, this a blowout happen. And one blowout, there's have to control management should be kicked on. So when try to kick on the control management, you see that the gas diverter is not working well. Ignition control fails, so they have ignition in the power in the generator room, and they start to have a multiple fatality over here with the explosion. But of course, when you go through environmental disaster, we had the block response plan is being applied, and the oil response plan also being applied. But because the huge impact, this system here failed to do it effectively because the volume is beyond the expectation. So the disaster is combination of both area, both element. Okay. So this is more or less the study of the 8 barrier being breached, one after another failure, then they have a blowout. Okay. And then of course, like normal, when we start from 1970, whatever, those accident that happen will create a requirement like what is the reaction, the new policy will come in, and after one other new policy. So the latest with Mokondo, and talking about a new policy will come in for us to strengthen the well integrity of our planning and our execution and our, of course, our monitoring. So as you know that we are learning, because we continue to learn as incident happen, we try to improve and learn from the incident to improve our well integrity understanding, to putting it in force, to manage the system and procedures. For safety critical equipment, of course, this is something that we have to consider to make sure they are critical. We have seen the statistic showing that tubing is one of them, followed up with the Christmas tree, with surface casing, triple SV, and so on. So let's look at the safety critical equipment. Okay. Like I mentioned to you, required numbers of barriers. Now we talk about 2 barriers. The 1 barrier is only on a very special case where you have hydrocarbon which is not flowing, like a tar. then you can put it there because it's not flowing hydrocarbon. But the rest of the hydrocarbon is actually mobile, and then you have then you need to barrier to able to sustain or to contain the movement or the flow of those hydrocarbon. Okay, then safety critical equipment, normally they usually the definition is an individual piece of equipment or a control system or protective device that is which is the requirement of a single point barrier. So we have one point failure should be they will cause an accident, result in hazardous situation. According to talking about if you have a failure, then of course you're going to have the damage done to your asset, to your people, and to your environment. Okay, and then the next, of course, this is the popular 13 item for the safety critical equipment. We're talking about the Christmas tree, which is the flow component at surface. Of course, the triple SV, the gate valve is all part of the Christmas tree element. You have the upper master gate valve, then the primary master valve, and so on. The flowing valve, all part of the Christmas tree, and the completion and production string is all wetted. Wetted means that this component will see the production of hydrocarbon. For example, when you see the production of carbon, it will be exposed to the element of any hydrogen, whatever content of the effluent of the oil, crude or gas, either it's going to be CO2 or H2S or mercury, or maybe you can have an element of sand. Sand components, when you're moving, it will just like a blasting effect to your surface element, causing the loss of metal because of erosion by the sand from the production oil or gas. But the non-flow method is something that is outside the flowing mechanism. That is, of course, but still considered important because if there's any leak from the flow wetted element, it will go through behind it, the non-floated area. So we have the wellhead system, the gas lift valve, which is outside the flow area, annulus surface valve, which is your whatever thing that you have annulus. And this, of course, the non-floated is not going to see the hydrocarbon, but it will expose to stresses due to temperature and pressure. And because this is outside the flow area, but they also experience the stresses due to temperature and pressure. Of course, the floated element, you have stresses from pressure and temperature, but in addition to the fluid itself from the reservoir. Okay, and then at the same time you have pressure monitoring equipment that to check all these elements here is to see the temperature, the tubing pressure, the annulus A, B, and C that we have seen the drawing, so that we know whether we are still within the range of safety of the casing design, the tubing design, or we need to do some control on the maximum allowable pressure in the annulus. Okay. And then, of course, as you go in the drawing, you can see the wellhead is around here, and the consistency also around here, which is the most critical part. You can see that most of the float is the wetted area. So we have the reservoir, this is floated area in the tubing, floated area in the triple SV, floated area in all the valves, going to the consistency and going to the flow line. And then, of course, critical equipment, because of the surface casing, is exposed to the environment, the corrosion from the sea, the atmosphere. And triple SV is very part of the wetted material, wetted instrument equipment. Tubing is wetted. Production packer also is a wetted thing. But it's unwetted, it's always around here. Production casing outside. And then production liner is also outside the flow. But still, like I mentioned, you're going to be exposed to pressure and temperature stresses. Okay, and movement as well. Because once you have temperature and some movement, the movement will get crashes with this element of non-wetted. Okay, for this is the system application. We were talking about the application that will help us to control the well integrity. It's all there in terms of the procedures, the recording, reporting, and then even nowadays they have the online system, the real time, where every activity of the well changes will be monitored on the daily basis, and then they can see the pattern of moving. For example, annual pressure increase. Maybe the wellhead growth also being checked, and then they're talking about maybe what happened to somebody running in with their login, so they can record those log immediately, keep it in the file, so people can do some studies and understanding what the changes from year to year, from phase to phase. So this is the software that help us to manage information about the well, and at the same time, it provide you all the guidelines, the records, the tables that you must follow. So objective of the well integrated management system actually to give a transparency on how risk is managed and to benchmark any of the operation that we are doing. Okay, and benchmarking against other operator is also very important because we want to make sure that, for example, our KPIs that how often we do the inspection compared to other operator, how often we do well intervention just to check some of the strength or the integrity of the well with those program, well integrity program, how we provide all the protection just for putting out the check valve, putting up something like, redundancy issues like redundancy equipment, like if this happen to this well, what is our option for a certain area. So all they been thought of. So they normally we share the knowledge with other operator. Normally the host government like Petronas, they organize this meeting so that we can share our experience, our problems, and how we solve that. So more or less with this knowledge, it helped Petronas, to have wells to be optimum production with minimum shutdown. Okay. Okay, data integration normally because when you have this system with the well information management system, you think about getting all the information from the system that you already have in house, and then you have your any of the Excel that you have been keeping for years before, you can put it in the system. So from the hard copy become digital copy, and you have all those other system that been recording your production profile, for example, your completion diagram is all being put in the system, and it becomes a center of references for you to really manage the well properly. So you can see that in the importance of this system to properly record and then store, and of course give you the summary of some study. You want to put graph, you can click graph from the records of the field, or try to compare from field to field into understanding the impact of or the environment to the well integrity. So integration of this from multiple sources of drawing is on. Actually, we help you to have the consistent well design to check record in the well. So you want to do the well intervention to the well, you can extract the information almost immediately. It helps to speed up the planning program. It start to help you to do the contingency plan, try to buy the material that require. What can be done quite quickly, other than firefighting. It's all last minute work. Then it to be a nightmare, because some of the equipment might be a lonely item. So you just can't wait too long for your equipment to arrive and have the shutdown, because you're going to lose production. Of course, you have to understand about well integrity tests in terms of the variation. You're going to be high, low, and then how we're going to test it. All the verification tests is going to be different, as we talked before. Operational data, talking about what have been done to the well, have the well been produced to, let's for example, previously to 5,000 psi, and now it's 2,000 psi. You can see that stresses is less. So is it going to be like any requirement to do some check whether existing configuration, existing casing spec, tubing spec is enough to handle the low pressure? But for us, we always consider there might be some high pressure untapped reservoir coming in soon. So you have to really check for this fresh pressure that's coming up from the new zone later on. So even though it's depleted, but you might be producing from the virgin area where the zone that is still not very, very fresh, high pressure is still there. And so event logging is also part of the requirement, whether you want to run check on the thickness of the casing, start to check on the scale development, and so on. So of course, you have a flow line, you have to put pressure testing on the flow line on certain depth, so that before you flow the total, when you flow the flow line, normally you have it water there. So any leak is going to be a water leak rather than oil. So you can test the flow line to the requirement operating pressure of the production itself. Okay. So of course, when we talk about well integrity, we have seen the well integrity chart, the people in charge. So you can see that when talk about responsibility, you know who is responsible for what, the art is responsible, who's responsible for each work scope here, who's going to be accountable, who could contribute to the system, and just and what party to inform. So information will be normally back to management, but responsible normally to the manager. Accountability is the people doing the job. Contribution is something outside the team that can contribute to idea in terms of information, in terms of studies, research, and so on, to support the accountable people to do the job. Okay, this is more or less something that you must have to help you to understand the responsibility and the accountability. Because sometimes the expert is on the accountability, but the responsible for the job is always be a manager or maybe the head of the department. So the head department might not have the authority or might have not the knowledge, but have the authority to ensure the job will be done properly as per procedure, as per policy. Even though he's not familiar, but he must be able to relate that to policy, guidelines, and procedures of the company. So the people in charge will be more like doing the programming. They must be also doing the everything as per program, as per procedures and policy. So they will have the endorsement from the responsible people quite easily. But anything happen, responsible people will be more chill, I would say. Accountable people will be punished or penalized, and of course the rest will not just contribution to the job itself. So normally, whenever you do a job, try to have a list like this to have the assignment, and then we have the people in charge, what each department is responsible, and then you can see that they will help us to really manage our work assignment much better. Okay, then we talk about the competency, because when we talk about competent people, as I mentioned to you, human barrier, we call it. So human barrier means that we must have the right people to understand the event integrity. So you can see that we start from the activity like well design, who's going to be like the expert. Of course, well design dealing with drilling, so they must be the expert from drilling to do that. And then of course for cementing, the expert from drilling, and all those barrier will be from drilling. But once you go to, annual pressure, of course, the well intervention, we're dealing with the annual pressure, then we have the expert from the well intervention. Then, of course, the expert also involved with well integrity. Yeah? You can see well integrity will be mostly covered on the expert side. They must be there. The team must be able to have the competent people. And of course, when we do about drilling a well, of course, some of the element expert from drilling will take place. So you can see a few of the experts still required within the system, which is mostly related to the well integrity, design and execution and well intervention and so on. Okay. And then, of course, what are the elements of when talk about the management system? We want to understand what is the content, the elements involved in the management system. So when we have a program or this is the application, the application should be able to, to relate the life cycle of the wells. You must be start recording from the beginning to the end. So, and then it will be a live document for the field to have all the wells recorded as we go along. Whenever you do a job, it will be recorded back to the system. So even life cycle of the well is actually coming from exploration development, and then we have suspended, and then we have the other well, the different status of the well during production. This is the well, this is cycle of the well that we need to have to think about covering in a well management system, the life cycle. And then, of course, organization chart will also be part of the management system to show you what's responsible, who's responsible, what's accountable, and so on. So they also be part of the well management system to understand the assignment of role to respective people. Risk assessment also will be more or less be defined in this application. They have a proper structure of risk assessment with different kind of methodology to evaluate risk in terms of it's going to be like high risk and what is the mitigation process. So sometimes they establish a very good structure or lesson learned that will relate that to risk assessment. For example, the moment you type your risk, then the system will locate to your database, showing you what is the remedial action, what should be taken, what are the potential, what you call it, side additional issue that you have to consider. So of course, we're talking about the we check also the well type with all the barrier, the envelopes, the second barrier, secondary barrier, and so on, and to control the hazard. Performance standard always define the requirement to maintain the well barrier within the operating limit. So this is the performance standard that is going to be really part of the well system to understand that you are going to go and work within certain limit. If it's too high, there will be some reaction to it, or command that you have to go and try to risk assess again the issue and then try to solve it. These are the performance standard of that barrier. Okay, web barrier verification and assurance process also be part of the application. And of course, at the same time, we're going to be having all this reporting, documentation, and then it's going to be accessibility. All the reporting, the database must be able to be accessed quickly, that we have the engineers to continue to do study about well integrity, to plan for their well intervention program, and try to see that, whatever been designed before is actually adequate, and they will more or less use that knowledge to apply for the new project to come, so that will be very useful with the WIM system to be very flexible and then very open in terms of easy access for database. Okay, so the cool toolkits for well information management system, we have, of course, the toolkit. Sometimes they put in like the well design package inside there to see, whether you put the casing there with the pressure rating. We have the burst pressure, casing pressure for the tubing, for the casing, the well design, and then with the well design, we tell you whether it's going to be cemented to surface, cemented to certain level. It's all being there. And then, of course, production data is when you produce the well. Of course, we're going to see, like, when you have scale, of course, the reservoir know that after this year, after producing for 5 years, we should expect the production of 3,000 barrels. But if you're less than that, then you could be talking about possible obstruction, maybe scale issues, or maybe some failure of your tools for the collapsed tubing, and so many things. So you have to check the integrity, once you have the deviation from your production data based on plan. Completion data, talking about the completion itself, the drawing of the completion, where we're talking about having the tools inside, the material for the tubing. Is it going to be compatible with the environment of production? So how you're going to manage for example, the tools that, for example, triple SV is very important component. How you're going to have the proper size, and what happens if this leaking? What you should do to be able to to solve the issues as soon as possible and continue producing. Preventive maintenance is very common. This is mostly covering the Christmas tree and wellhead. And of course, the maintenance is going to check what the condition of the tubing, whether the tubing is still having the full access for production, or start to have some issues with scale in the tubing. Of course, you're going to record a maintenance result as a database of maintenance issues, a solution that they have done, so that will become a lesson learned for the project itself. Roles and responsibility, actually to know who's going to be responsible for the job, who's responsible for the planning, endorsement, authority, approval, and so on. And then the facility status, talking about, if it is talking about related to the wellhead, the flow line itself, and at the same time, we're talking about the growth of the wellhead. So it's going to be a concern. The well failure model, normally we're talking about if we see that certain environment, pressure increase, or for example, the production down, what will happen to the possible failure? And the failure model will also try to understand what is situation, where if you have a leak in your tubing, what is going to be your reaction or your proposed remedial solution to that. So well failure model become important. I think we cover that in the specific topics session coming up, I think by tomorrow, hopefully. Okay, so the toolkit, as you can see again, same thing. It's called about the barrier for well design, and we're talking about annulus pressure management here, compression design. We also give us, because of the leak of the tubing can cause a different maximum allowable annulus surface pressure, And then we see verification system here, this detection technique here, and then who should do the job is on the role and responsibility. This is info management for the facilities and so on. It's about documentation and how urgent the failure correction. So this is the failure model. Okay. Okay, anyhow, you can see that all this information here will be shared with you in our video. So I think you can go and repeat, try to review again whatever it be missed out, so that we can see how the information here actually help you to understand further, and even you can explore further from the internet on the subject. Okay, so I think we're going to have a short break very soon, but let's continue until the end of the section. So I think I will give you about 10 minutes break. And of course, I think during this 10-minute break, you have any question, you can post it to the chat column here, and then I try to answer as much as possible. Okay, I'll see you about 10 minutes from now. Thank you. Assalamualaikum. Fine. Assalamualaikum and okay, good morning. We continue again. So now we're going to go for well integrity surveillance. Now that's on this part. And of course, well integrity surveillance, you can see the features for the surveillance itself. We're talking about the status, and now we're talking about the well barrier status, the overall integrity status, the analysis of the casing status, the valve status, and of course we have also how we do monitoring, and then how we deal with the details of the well itself, and then in terms of any logs that we run in, if the log is showing that the well integrity is an issue, what we should do. The reporting is also important. So these are the features of the WIMS that we should continue for the surveillance. So we talk about, for example, integrity well status. You can see that we're talking about the well reach status talking about the level of the risk that we are encountered in this well. At the same time, the integrity status coming from the risk assessment. And of course, when we talk about the barrier status, we're going to check on two barrier status during the surveillance, whether going to be any two barriers being in place or not. If one of the barrier fail, then we have to depend on the secondary barrier and what's the next step to restore the primary barrier in the well. So it's all been planned, based on the surveillance of the well. So at the same time, you're talking about status of the annulus. We've tried to continue reporting, and then if there's a potential of annulus pressure going up because of thermal effect, there'll be some mechanism like a check valve to be installed, or is there going to be like a squeeze job or cement or squeeze job in the annulus to stop that, or maybe talking about some of the elements of bleeding off continuously. If the pressure start to be like uncontrolled, then we talk about continuous bleeding out the annulus, and put it something like a small line, like choke line, or not sorry, kill line, control line, going down to below the seabed to release any gas that is continually coming in. So there's a lot of option available, and surveillance will help us to understand what are the steps to put safety, protection to the well or to the platform itself. The valve status, since the valves become the key components of the wetted material, wetted flow from the hydrocarbon, we know that the valve itself being exposed to the disaster, we call it. You have the hydrocarbon, we can have CO2, we have H2S that can attack the valve very quickly. So there will be, because valve is coming to surface, it's at the facilities in the platform itself. So that's why the valve is exposed. So there must be a proper maintenance check, understanding about what are the specs for the valve. Is it going to be standing the stresses of the fluid that we flow on? Also, with well monitoring, we have to monitor the well to understand that the well is going to be still stable in terms of the casing, the cement, that should be able to control the cross flow from hydrocarbon zone to another zone. So there might be some protection to that. And well details we cover, for example, the specs, the design factor of that, and then we're talking about whatever requirement for for us to look at the integrity of the well as to understanding the specification, how the well be designed, and factors that they consider. For example, some well be designed to handle 20% CO2, some well designed for 40% CO2 content, and so on. So there will be a lot of details that need to be known about the well, so that be kept in the system. Okay, non-conformance logs normally WIMS indicate that possibly to connect a company system for handling well diagnostic. So this is more or less some of the correlation from our system to whatever being the input coming in from outside. So as then the reporting is also important, that once you have all the features here, reporting become important to be able to store in the database and to record it for the next plan. For example, when we're done to do some well, they're going to go back to see some references where they understand which one is the operation procedure or guideline that give them the best. So for example, normally some activity need to have a check run. Some activities need to do some bleed off requirement, to check the integrity of some of the barrier downhole. So all that had to be done properly, okay? So for example, the one example, for us to check on the corrosion rate, for example, the material that we install have to be, then we can see the impact. For example, we have installed the chrome material, the alloy material or tubing. Then based on the understanding, there will be a requirement for the material is set to withstand certain environment. If H2S is certain height, and H2S plus CO2 or CF plus CO2 plus salinity brine, calcium or sodium, then the impact will be different from one another. So the check will be normally most of the supplier of tubing, they will have a chart showing that what they have been tested in the lab for the material of the tubing that we purchased to withstand. So we can refer back to the manufacturer to understand the corrosion of the material that we purchased. Okay, annular pressure monitoring is become important. As you know, annular pressure, like we have seen, can cause a disaster of collapsing and bursting of pipe. So the presence of high H2S in a well associated with a high leak rate is very common. So unless the material selected is proper material, certain alloy, then we protect the H2S doing the damage to the tubular. Okay, so where is ranking? Normally, you can see the automated ranking coming up from the system. They can even do some risk ranking based on our input. Corrosion analysis also can be done through the system. Some system have some of the well integrity management system have some sort of like a corrosion analysis where you put in there based on the statistics or their database library, based on the manufacturer, they can give you some idea about the corrosion analysis or the tubing that you run in based on the condition being exposed to the tubing. Of course, at the same time, the system also produces the risks. We should be able to monitor all the annulus and all the bleed off event if we need to do that. So all this being captured by mostly the system. For example, if we buy a system from company A, for example, they have been collecting a lot of information, studies and information throughout the world. And so they come up with a certain very unique information about, the whatever chemical reaction, chemical whatever, how to handle annulus, how to do the bleed off of those high pressure annulus is in the system. It helps you to make a good decision itself. Okay. And then we're talking about the integrity surveillance. I think we have covered that already. The surveillance of those integrity. And triple SV, as you can see that sometimes this company or even a group of company, they come up, for example, Shell and ExxonMobil or even Chevron, they have been having all the triple SP. They can see the mean time between failure, how often they are failing. So based on the manufacturer, they can have a plot. So we can see that what are the best solution manufacturer for the triple SB. Or sometimes you see that you'll be able to select some or triple SB, and then we can put it on tubing retrievable, and we can replace after 10 years, for example, or 15 years. Because normally after 10 years or 15 years, we have to look at the condition. If the well is dying off, we put it off. If it's still producing, we can decide whether we have to recomplete the well so that it come back to the original strength of the tubing to continue production. So triple SB is an analysis on what are the company that provide the best tools for a long life or reliable tool for integrity. Okay, so normally in our system here, they might be able to help us in the drawing. So for example, sometimes we have a consistent drawing, so everybody will understand the style, which one is triple SV, which one is the primary, gate valve, wing valve, and then all this lower master valve, all this term here, we tell you that this is the component exposed to the wellbore and its potential failure is quite high. So we have to check with integrity. At the same time, we have the annulus A, annulus B, annulus C. We have to see whether if the pressure is under control, then you can have a normal pressure gauge to monitor and being reported daily basis by the production engineer on offshore, and then put in the system for us to understand whatever the status of the wellbore with time. After 1 week, 1 month, or 1 year, we can see the pattern. If the pressure start to show some indication of extreme, then you have to think about all this annual pressure have to be managed properly by a bleed-off system or by doing some repair on the annulus that is causing the leak of hydrocarbon to the annulus. Yeah. Okay, this is the schematic of the drawing. You can see the drawing here is showing that a conductor, you have a cement cemented to surface, and then for this casing, the cement is also cemented to surface. But this casing, the cement is cemented halfway. It allows some gap here for any high pressure to be bleed off here, you know. So that's why I think the reason of having it here halfway to be able to provide a passage for pressure to bleed off. The same thing with this production casing. You can see the cement is being set not to surface because it allows some space here for any annulus pressure to bleed off. But in our design in Malaysia, knowing that most of our reservoir here is normal, we cemented the cement inside the casing so that we stop migration of any hydrocarbon to surface, and at the same time we are able to protect the casing from any other influence from the reservoir. So that's why the practice in Malaysia, we normally have the cement inside the casing, and then do not allow any reservoir to come in. But this system here is actually providing a bleed-off point. If the any pressure annulus, it will bleed off to the formation. So this is a different style, different requirement, but it depends on the policy of the company. Then this is where we go to handle the well design. Okay, sometimes in the system they have certain codes, as you know, certain codes so that they will understand each other. Talking about codes, we talk about if another status is a different code, and integrity status is different code, and so on. So the when event, the log will be called the first when we spark the well, drilling the first surface hole, then do the drilling operation phase, the production phase, then we have the servicing, the intervention is all under the same category, and then we have done well unlock. So all this will be more or less coded, so we know that how many times the well have been seeing the wireline state line job, and then when is going to be a visual inspection done for discrepancy and so on, and then monitoring of the wellhead reading, the database, the analysis by the engineer, what is the conclusion, and the status changes. For example, some well have been producing and be shut down for a while because they need to do some reservoir management. Sometimes the status, for example, one well is under oil producers, and then they change it to water injector. So all these changes might be recorded, and we have to review the well integrity issue with these changes. Audit normally we come in to check whether we have followed the instruction, we have followed the policy, and whether what is being checked being properly or being more or less recorded. And at the same time, they always go through the the inspection report and see what action being taken. If it's not being taken, it means it's a failure for the company too. So the audit itself is a very important process to check and balance our process and execution plan. Okay. Of course, in the drawing of in a wind cell, there must be a proper drawing that share the drawing cell, which is telling you 1,000 stories. So this will show you what in terms of the elevation to your heli deck, your working level, and then you have your wells and you have your casing schematic, and they will show you what are the cement top here, and then normally they will show you the temperature. Normally they can have some logs that will record the temperature gradient. And all these other parameters of the well can be plotted in the well. You can recall those data when you want to do, any jobs for this well. So this data sometimes you keep alive. So in other words, you can have the data for example, for January, then February, you might have another data. So if there's no changes, of course, they keep on, maintaining the same drawing by putting a note that this is the same as before. But once they have changed your data, they are going to see the changes in all the annulus pressure and then the changes in temperature gradient. They will see that in the drawing, like a database. Okay. And then of course, configuration of the well, you can see that what's the component of the well, the detailed component. And over here, they will show you the material being used. And all this will be part of the correction program that we're talking about. At the same time, we show you the specification of our pressure strength and burst and collapse strength to guide us for the annulus pressure management. So all these detailed drawings actually showing you the drift ID and what are the minimum passage that we can pass through. We can check on the scaling itself based on the dimension, the ID of the tubulars inside. Okay, so barrier schematic also become important. Most of the WIM system, well information management system, will have a drawing that show that will identify the barrier. So mostly the barrier schematic is very important because this is when the audit will come in and check whether you have the two barrier system at all time. You know, so all the system. For example, you're talking about this annulus. Is there any two barrier system in the annulus? And the tubing, is there any two barrier system in the tubing? Annulus here, option is going to be a two barrier system here as well. So the barrier system here will show the health condition of the well. If one barrier fail, then you're talking about you need to do, you still can produce, but with certain limit that before you come up with the remediation to establish or restore the failed barrier. Okay. And then talking about the input data, review data is quite common. We have all this annual special management, well integrity, and this is the, I think, integrity test, whatever, and then this all the other tests as well. So you can see that the risk assessment will be a question here, risk assessment consolidation. Consideration, then I had the technical data before, event, failure, or whether failure history. All this will be input to the system, recorded, and then of course there will be some implementation for remedial repair jobs as part of the information that being put in. So if the well have a good health, production can continue. If there's any issue, they have to shut down the well, stop production, and do the repair job. So repair job normally come up with in group. You have some time not to spend, because you come to the platform, you normally be involved with some heavy lift, you have to shut down the well. So the word shut in the well is not a favorite subject. So that's why you have to come with group so that once you go in, do the rigging up with heavy lift, you have to shut down the well and it can work on 3 to 4 wells to be more effective to handle the production shutdown. Okay. And of course, for well integrity, there's a minimum requirement. No? For example, you must have the accountable person in charge. You must have the procedures in place. You have the well intervention guidelines so that you know when you enter into well integrity issues, make sure the integrity is there. And if you find out any failure, they have to restore that failure, restore that barrier before you continue with your intervention. And of course, the tubing casing integrity is related to the corrosion rate, and so on. And then Christmas tree maintenance, because they are the sensitive areas at surface where any leak can cause disaster. You see, imagine the disaster that we have, and mostly, coming up with the failure of the testing tree not able to really hold the pressure. Okay, and all other things like the downhole safety valve, this is mostly the annular surface valve. It's all the part of management required for your integrity standard. And knowledge management, talking about all this lesson learned and so on. Okay. Okay, now we have, for example, this available software for in the market now. You can see there's abundance, but normally every software we have we call it their advantages and their strength. And for small company, they will go for something that is just enough to fit for their requirement. For big company, they're talking about overall system. They're going to be willing to pay for expensive software, and and then will help us. But so far, you can see that the most popular, so far we have this Peloton. I have two versions here. And then, of course, another one is, I think another one is coming under Westcape. It's another one, popular, expensive, but normally have multiple function, a good database system, and it's going to help the company to manage the well integrity much better. Okay, I think we're almost to the end. I think we just cover one risk assessment. Risk assessment, as you know, going to cover what is risk. The risk is the possibility of something bad happening. This is and then example of what are the hazard and risks is that the frequent bending of the tubular, and then risk is like this example, and then the manual handling of injury at the back. So we too high. I mean, some of the boxes. So that's the what is risk, something that can go bad. So risk assessment, we have to consider location, like is it going to be like offshore or going to be like manned or unmanned platform, proximity of the area population. And then, of course, we're talking about the outflow potential, how the hydrocarbon can flow and cause problem to the environment and to the equipment as personnel, and of course to the asset. And then we're talking about redundant system. Are going to be like, for example, you have an issue like possible risk. What happen if the risk happen, issue happen? What is your preventive action and your mitigation? External environment, talking about the corrosion from outside, how you to manage that corrosion. There's a few suggestions from the literature, from the industry experience, how we manage the external corrosion, of the well. Okay, and then of course risk management process. We can see that the risk management process covered, like we have to identify the risk, and then we do the assessment, and we try to put in the mitigation plan, solution, and then we implement and monitor what we have done. This is the risk management review, and then we update the plan itself. So we're going to cycle. So risk management can go to very complex risk to a very simple risk. So when it become complex, of course, there is more thinking, more discussion, asking for expert review as well, to be able to make the right decision and not to look for failure in our planning or our decision making. For risk management decision, you can see there's a few areas of the understanding that we have to, before making decision on risk management, we have to follow a very few steps here. Okay. And then for the metric itself, managing the risk, normally we go with the metric system. I try to find the limits and try to really act based on the requirement. So you can see some of the chart here to evaluate for the risk. Now we have probability of happening and the consequences. For example, if it happen, for example, we have number 4, level 1, 2, 3, 4, and this is high, this is low. So in sequence, the impact is high. Then we have to make sure that we try to see what is going to probability of happening. So the what happened when you talk about all the red number here is talking about try to avoid it happening, because the impact of damaging is huge and the probability of happening is very high. So in this case here, we try to say that risk is so high, is not unmanageable. We have to consider really doing something different, even like killing the well, abandon the well, or do not do any operation that dealing with that area. But once you are in this region here, or the region here over here, then it's manageable. Like for example, it's high risk impact, but a very low probability of happening. So it's still between like 5 points here is okay, 8, but not 10. Anything 10 and above is bad. So the number here is showing that it's comfortable here, it's getting less comfortable but manageable. So this is, once we have this risk analysis, risk matrix, based on the company policy, then you see that in anything that is above 10 in the calculation here is no go. So talking about, you have to think about the solution. Otherwise, you're going to be more or less like look for abandoning the well, no more dealing with with potential hazard and so on. So that's the risk that we're talking about, how we do the evaluation. Okay. The risk bubble is that, we know, for now in the planning stage, especially when you know that you have the risk or high number of risks, for example. So this is the safety zone here, and this is the danger zone. So you're talking about if the well is coming within the uncomfortable zone here, you try to reconsider the mitigation, whatever the alternative that try to push the risk based on your mitigation program, based on your design factor. You can move most of the design here back to the comfort zone. Here is much more comfortable. This is comfort, it's uncomfort. You try to push those risks in the uncomfort zone to the comfort zone. Then you can implement those mitigation process. Okay. So that's how. Then of course, risk consideration over field life, talking about from the drilling space, and talking about the risk analysis here. Whether you want to drill a well or you don't want to drill, you cannot drill the well. It's all based on the risk analysis. Sometimes you're going to encounter so much risk and issues. So it might be you say that it's not economical or worth it to go for the lower zone. just concentrate on the the upper zone, which is normal pressure, for example. Huh? And then we have during completion, you have another risk involved here. You do analysis, whether what you should do, what you shouldn't do. And then during well testing itself, during the production well, you have also issues with risk. Evaluate the risk, consider what is the level of risk, and then try to mitigate and reduce the risk from high to low, and so on. Okay, and then I think the risk for the life is going to be more or less the same. How we going to, for full life of cycle, we should be able to consider the risk, like the drawing, like we discussed about, the previous drawing here is about the same subject. And then, of course, environmental factor, risk over well life cycle. They're talking about all these requirements that when we design for the risk assessment, we have to talk about the environmental effect, of course, the life of the people and the asset itself, the damage to the asset. Okay, so this is another one. I think this is more towards when we drill the well, we have the issues of pressure coming in, and of course the potential hydrocarbon issues of the risk to be analyzed. Okay, so I think we end up for the class today. Tomorrow we're going to start again at 9:30. So we will cover the remaining 4 hours. I think the third section here, we cover the well failure models. Then we have the barrier construction, restoration, and then we verify the barrier, analyze pressure management, which is very interesting. And then we're going to get the checklist for the third session. I think for the last section, we're going to cover most discussion about the global, integrity issues in some other subject. Okay, so hopefully you will have most of the slide, understand about the slide more or less. And then if you have any question, you can still note down to in the chat column. Then we can to more or less see you tomorrow, 9:30, and then hopefully we will cover the third and fourth section, another 4 hours to complete our course. Okay, so thank you very much. And Assalamualaikum warahmatullahi.